Okay, today I want to clarify a few concepts because I think from the responses in the discussion board that you're not quite understanding the difference between what a hole in the graph would be for a rational function, or any function for that matter, as compared to what a vertical asymptote looks like for a function. So we're going to study this one that I've created over here, and take a look at what the concept is in general, and then also compare the graph to what the table reveals, because sometimes you're going to only be provided with a table of values, and I think that these concepts are rather uh, easy for someone to recognize given a graph, but you need to make the same type of inferences about the behaviors around particular input values if you only have a table. So we're working on the multiple representations of a concept here. So firstly, we're going to call a hole in the graph is something that we call a removable discontinuity, because you could kind of just think about it like a hole in your tire. You can plug it up, patch it up, and keep it moving. So that's kind of why they call it removable, because if we were to fill the hole, we'd be okay. So think about this as like if you're on a roller coaster, if you're traveling on a track, there's all of a sudden a break in the track and then you can't get to the other side. So that's kind of what the difference is between a hole. Or if you're driving on the road and then there's a pothole and or a sinkhole and you can't cross. So that's kind of the difference between, well, that's what a hole looks like characterized. And then visually in a graph, that is. But a vertical asymptote is something different. A vertical asymptote is a value that a function is going to get closer to, but it's never going to exactly get to that particular value. It will exhibit some sort of divergent behavior. Like it's going to infinitely try to get to that number instead of just breaking at that particular point. Whereas if I'm at the hole, I'm going to approach and head towards a particular y value. So let's just say this is y1. And then if I were on the other side, I would be able to see that from both directions for this particular input value, from the left of the input, I'm headed towards this y value. And from the right of the input value, I'm getting closer and closer to a single number. So this is different from the way that we would be able to analyze number patterns, because it's going to head towards a single y value. So maybe we could say, as we approach x from the left, well, we'll just say we'll just call this like 2 and I'll call it 5 as an example. So we'll say as x approaches 2, and we would use a superscript of like a little negative to show that I'm coming from the left. I'd be able to answer this with a limit, and let's just say that this is some function f of x. So the limit of this function as I approach 2 from the left is going to be 5. Understand that f at 2 is undefined. A limit can have a value even though the function doesn't, because a limit is just saying where is the direction of the graph going, what is it headed towards, whereas function evaluation, that tells you specifically what the function will evaluate at. So in this case, I can see that f at 2, in this example I have created, is undefined because there's a hole at that particular point. But when I approach the graph from the left of x equals 2, I'm still headed towards that y value of 5. And then if I were, and let me just further, I'll just say, so from the left, I'm headed towards a y value of 5. Now let's say if I want to go from the right, if I want to say what's the limit of that same function as I approach 2 from the right, I'm going to also get 5. Because as I go from the right of positive 2, as I'm headed towards that x value of 2, I'm still headed towards a y value of 5. So even though the function doesn't exist there, my limit shows that I'm approaching the same y value, and if the function were defined there, it would be 5. Now, for the vertical asymptote, let's say that this particular x value is 8. Well, if I study the limit of, and let's call this function f of x as well, the limit of this function as x approaches 8 from the left, what is my answer going to be? Well, let's think about it. As I come from the left of 8, I'm going to be coming on this side from like 0, 7, 7.9, 7.99, 7.999. Notice where the graph is going. It's not going to a single y value. It's headed towards negative infinity. And then if I were to say, what is the limit of the function as x approaches 8 from the right, so a superscript of a positive sign, I'm going to go from the right of 8, which means I'm going to come from like 10, 9, all the way to 8.00001. And notice the function is going to positive infinity. Of course, you would just write infinity, not the plus sign. I'm just doing it for emphasis. So we would see that there's this sort of infinite behavior. So it is approaching that x value, but it is diverging to infinity or negative infinity. So when your limits are when your limit answers at a particular input value, not in behavior, when they are approaching those values and the answer turns out to be infinity, that would be a way for you to know that there's a vertical asymptote. And again, if I were to say, what is this function evaluated at 8? The answer would be undefined because there's that asymptote there by that broken vertical line that I have drawn in here. And we can see that that function doesn't exist. So a lot of you were trying to make the claim in your discussion board that if the function is undefined, then that is automatically the evidence that you need to know that there's a vertical asymptote. Well, that's enough evidence for us to say that there's a domain restriction, meaning that these particular input values do not exist in the function. But for you to take it a step further and say that it is a vertical asymptote, you would need to provide a little bit more evidence to clarify how you're able to make that inference. And that's what we're headed towards. Those are really good things to be able to do, but it takes a little bit of practice. So in this case, you would be able to compare the answer to the limit questions. If I'm approaching an input value and from the left and right, I'm going to a single y value, then that means there's a hole there. It's undefined, but because I'm still trying to go to a particular y or output value, I'm able to say that that's a hole. Whereas when this is undefined, it's not going to a single output value. It's either going to go to infinity or negative infinity as I approach that particular input value. In this case, it was 8. So it's diverging. It's going off to infinite land. So when that happens, that's how we know that there's an asymptote, because that's what curves do to vertical asymptotes. They approach them and get closer and closer and closer and closer, but they never actually reach them, and they will continue on that journey forever. Whereas if you have a hole, you're going to get there and then you're just going to stop at that value. And then as soon as you're right past it, you're going to pick up and keep going. So there's the difference between what a vertical asymptote and a hole is. So let's make sure we can understand what that looks like for a function if we have a table. And we're going to start by comparing the values here. And to reiterate, I have another function that I've typed in here for you. It doesn't matter what it is, because our goal is to just simply say, what can I recognize from a data table? But just so you can see it here, the connection will be made to the graph. So I'm going to say at x equals 5 and at x equals 3, you can see in the table that I have created, it says that the function at each of these input values, 3 and 5, is undefined. When you look to the graph at the right, one is a hole, one is a vertical asymptote. So simply stating that the function is undefined at a next value tells me that there's a vertical asymptote would be loaded with an error already in the reasoning. So let's compare a little bit more. Now, I have filled in what that asymptote looks like and that hole. When you're looking at these functions in Desmos in the future, because we're going to be studying these rational functions, they're not going to appear. It'll look like this. And so if you were to zoom out, you would have to look at something like this and see that there was some sort of asymptote here, because I can see that the graph is trying to get closer and closer to some value. And as I zoom out, it looks like it's getting closer to it and making it there, but it doesn't actually reach it. It's going to infinity land. So this is how we're able to see it. We're going to learn algebraic or by hand methods. Of course, we already said in our lesson yesterday that if you take your denominator and set it equal to 0, those are potential locations as to where you could have a vertical asymptote, but also a hole could produce from that as well. But it would still give you an indicator about which one of the input values that happens at. Now, when you're trying to identify a hole, we're going to have to know a little bit more about these and I'm telling you today that it will be at 3. But notice that as I take my finger or my cursor, you would click on the curve, and it doesn't show a hole in Desmos as graphed until you get closer to it. So notice my values. Once I get to the value of 3, then the hole shows up. As you see, it says 3, undefined, and then a hole shows up right there. But once I go past it, it changes. So let's kind of study what those output values look like, and then we'll make the connection to the table. So if I'm right here at x equals 3, we see it's undefined, but let's go to the left of 3. As I back up from it, 2.99, notice the y value is 3.693, 3.637, etc. I can see that it's headed towards a number. It isn't going to infinity. It's headed towards a single number. And then when I cross over 3, if I were to come back that way and get closer to 3 from the right side, like I was showing in the limit problem with the highlighter, as I get closer and closer, you see the numbers dropping from 4.3 and it's dropping down to something close to 3.8 and then 3.6 on the other side because it's undefined. So that's kind of where we're getting this value here for us to see what the hole is, but I'm able to at least infer that I know that a hole is happening because around that input value, even though the function is undefined, I can see that the values for the outputs are headed towards a single number and not going off to either really large infinite positive numbers or really small negative infinity type of numbers. So let's look at that in the table. So I'm just going to remove 5 and 3. And so let's just say we'll just come to it. So we'll say like 2.5. And then in the next one, I'll say 2.8. And then 2.9. And then 2.99999. And keep making more 9s. I'm getting closer and closer and closer. And then I get to 3 and it's undefined. Now I'm going to go a little bit beyond 3. Super small, and notice that I'm starting to see another little bit of a pattern as I move away from that value. So if I analyze the table, hopefully you can see at x being 2.5, it starts at 1.8. As you get closer and closer and closer to 3, notice that the value right before where it's undefined says 3.74999. That rounds to about 3.75. And then so if I were to say there were a vertical asymptote, I would be looking for that number right before 3 when I'm super close. Not like at 2, but the 2.9999999, like I'm right there. When I'm that close, if it were a vertical asymptote, I would expect that number to be humongous or really small. Like I would expect it to be like negative 500,000 or positive 700 million, something like that. That would give me evidence in a table with number patterns that it's going to infinity without the word or symbol infinity being written. And then notice that right after we get to the x value of 3, the next data table value for x will be 3.000000, however many zeros I type 1. You see that it picks up right again at 3.75. So it looks as if the table is saying, oh, I really want to get close to 3.75 when the x value is 3, but it just doesn't make it happen. So there's like a little pothole there. But we could see right before and right after x value being 3 that the y value, or the output values, are approaching a single limiting value of 3.75, which would be the case for something like this in a whole. I'm headed towards a single number. It's 3.75 right before, 3.75 right after, but when I'm exactly at x being 3, it doesn't make it there. It's undefined. So that would be a removable discontinuity, which we could call a hole. So now let's see what would happen if we were to look at the pattern for the asymptote that I have graphed here at 5. So let me turn that on and get rid of this point. So if I want to see what does the table tell me about the function around that, I'm going to create the same type of idea. What happens a little bit before 5 and what happens a little bit after 5. So let's just jump right into it. 4.9, 4.99, and just get closer and closer and closer and closer and closer. Then I see it's undefined, then go slightly past it. And you can see the pattern here. When we're looking at these values, it now moves into scientific notation. So remember when it says, like, for that 4.99999, it says times 10 to the 11th power? That means I would move my decimal place to the right 11 times. So therefore, we would have that huge number. And then when I'm also looking at beyond it, 10 to the 17 says move that decimal place 17 places to the right. So it'll be 3, 5, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, and then 0.0. So you can see that even though it doesn't say the word infinity, you're seeing this unbounded behavior. And when we just analyzed the limit, we said for a vertical asymptote, the function is going to either approach infinity or negative infinity when I'm hovering around a single input value for me to make the conclusion that there's a vertical asymptote. So even though it doesn't say infinity, because I can see these really large numbers on either side of x being 5, that is the table evidence that I would cite for me making the inference of this function having a vertical asymptote if I didn't have the function to actually convince somebody of. We would just say, well, from the table, from the left of x being 5 and from the right, the outputs are approaching infinitely large numbers. Now, of course, that's for this particular case. If we changed it to where they were going infinitely small, or it could be both directions. It could be like negative 700 million on the left and positive 800 million on the right. It doesn't matter. They can either both go in the direction of infinity from the left and right. It could both go to negative infinity, or it could go to negative infinity, then positive infinity, or vice versa. The fact is that when I'm getting closer and closer to the output value, to the input value, I start to see this unbounded behavior. Unbounded meaning the numbers getting really huge, really small, as compared to when we saw the whole. They were headed towards a single limiting value, a single number from the left and the right. Not a really huge or really small number from either side, but a single number gave us a whole. So that would be the table evidence that I would hope that you would look for when you're trying to convince someone of whether or not there's a whole or vertical asymptote in a graph. And then the next thing that I want us to consider is when we are looking at the horizontal asymptote. Now, we never really cross vertical asymptotes, but it is possible for a function to cross a horizontal asymptote. Not all the time will it, but it can. But the main idea of a horizontal asymptote is to give us some information about what the end behavior is. So these are questions where we would say, if I were to now say as x approaches negative infinity, for a function. Or if I were to say the limit of this function as x approaches positive infinity. So notice the difference here. In the previous examples, we were approaching an input value. That means when I'm at a particular x value, what is y doing? And then we had these different answers. Horizontal asymptotes are when we look at end behavior. When I go to the left forever, or if I go to the right forever, what is the function doing? And let's just say that this is 3 as a y value. You could see that these y values are getting closer to 3 on the right and closer to 3 on the left. So therefore, we would say as x or input values increase without bound, the outputs approach a value of 3. That reinforces a horizontal asymptote. Or it could approach any other number, but the fact is it's approaching a single number. Whereas if we had this divergent type of behavior, we would have something that looks like this. And we would say that the limit of a function as x goes to negative infinity is positive infinity, or it could be negative infinity, etc. But the fact that these values, when I go to the left forever or to the right forever, I would see my outputs growing or decreasing forever, not headed towards a single number. So, for instance, if I had a table and I had negative 100,000, negative 1 million, I would start to see really big numbers for this model here. Like it would say, I don't know, 7,000, 950,000, like something like that. That's what table evidence you would see. It's not going to say infinity, but it's going to show really, really large numbers as we go to the left, which is how we would make a conclusion or an inference about it being infinity. Whereas in this case, when I'm looking at the function as x approaches positive infinity, I would see that these numbers, because it's going down, I would expect them to be really small. So if I were at 100,000 or positive 1 million, I would expect to see maybe the opposite. It doesn't have to match, but it could be like negative 12,000, negative 450,000. I'd start to see really, really, really small numbers, which indicates that it's going to negative infinity. If they were growing to huge numbers, we would say they're going to positive infinity. So there wouldn't be a horizontal asymptote in this, because at the end of our table, as we decrease x values without bound or increase x without bound, meaning go to the left forever or the right forever, I'm going to see these numbers growing huge or small. Whereas when you have a horizontal asymptote, if we were to look at a data table, the extreme ends, for instance, negative 1 million, this would look like 2.999. And then over here at a positive 1 million, you would be seeing the same thing. Well, in this case, it would be bigger. So it would be like 3.00001. So we would see that they're headed towards, the ends are headed towards a single number. So that would give us the evidence from a table to infer that there was a horizontal asymptote, because it isn't unbounded. It's not going to huge positive numbers or really small negative numbers. So those are the differences in what you would look for in the patterns as to make conclusions about horizontal asymptotes. So if we bring this back to our Desmos function that we studied over here, let's see if we can determine what our end behavior would be for the function that I have typed in here. So as we scan out, it looks like this is not going to be going to infinity or negative infinity. It looks like there's a horizontal asymptote here. And so I want to know, well, what is that horizontal asymptote? Well, in the table, again, let's say as we go to the left, I'm going to type a really large number. Let's start off with 100,000. And you can see that it's 0.999, which is almost 1. Let's say I make it larger, negative 1 million. It's even closer to 1. So let's skip a few. And let's say if I were at the other extreme of the table, when I'm going to 100,000, it's a little bit above 1. And if I go to 1,000,000, it's still a little bit above 1. So it tells me that the ends are headed towards 1, which would be table evidence to use when you're saying that there's the existence of a horizontal asymptote, because as x increases or decreases without bound, the output values head towards a single value of 1, which tells us that there is a horizontal asymptote. Okay, so hopefully this will allow you to analyze these tables a little bit more precisely than you were doing before. And I hope that I have maybe clarified some misconceptions in the understanding about the differences between a whole and a vertical asymptote and just having a value that's undefined. Yes, they are both domain restrictions, but the table evidence that you use to tell me one of those exists is quite different. So I would like for you to take a opportunity to respond to the discussion board below and see if you can come up with the answer to the limit questions about whether we have any vertical asymptotes or holes and what the end behavior is for the function, provided the table only. You don't know what the equation is, you don't know what the graph is, so you're only going to look at the table as evidence to make inferences about those types of discontinuities or end behavior questions.